up and over, please. And actually, well, there's a couple things. Let's get those up and over. Have your note packets out. Pens and pencils should be down. Have your note packets out. What page did we leave off on? What page did we leave off on in the notes? Was it 6?
Probably somewhere around there.
Yeah.
All right. Before we do that, though, it's not letting me open the program, so there's not going to be a way today, but it's not really that necessary for you to log into your calculators. What I do, though, want you to see, are they all in? Here's what our answers are, and here's how we would go about getting them. The first couple of them, I hope, were pretty easy. We should be able to clearly identify that the square root of 64 is going to give us a 8, and the square root of a to the 6 would be a to the third. Because remember, what's the implied index on a square root that we don't write in? 2. So we're seeing how many times 2 goes into those values. This would be once with the remainder of 1. Same thing over here. Questions on any of those first 3? Let's take a look now at a question. I guess here's the remainder of them. Some of them were more difficult, like question 7. That's kind of tough. What's the perfect cube that goes into 24? Hands up, please, if you can tell me that. What's a perfect cube that goes into 24? Terrific. 8 times? 3, yeah. And the cube root of that would give you the 2. Does 3 go into x to the 8? But how many times does 3 go into 8? Twice, with the remainder of 2, because 8, it doesn't go to 8, but it goes into 6. So that's why those break down into what they do. Hopefully we all got number 5 right. The radicand can be negative when you're taking a cube root or any odd root. Same thing, look at number 6. 6 should work out terrifically. Negative 8, take the cube root of it, I'm left with negative 2. Then I'd have an x squared and a y to the first. Questions on those? And then to end with, on the back, oh, that was somebody else. That was all of them? Oh, I didn't get the back, I'm sorry. Well, those were 2 of the papers that we had from the first group. All right? So, the next thing that we're going to have us take a peek at is this. Have out your homeworks, please. Actually, let's do this first. Go to your function of the week sheet. I'm sorry. Then we'll do homework after. We didn't do one last class, is that right? Okay. So, for today, this is week number 2. We're going to do, and we've been working with radicals, so we're going to graph out the parent function y equals the square root of x. That's your parent function. Now, who can give me one ordered pair that's, don't go to the calculator. What's one ordered pair that's going to be on the graph y equals radical x? Any of them. There's an infinite number of them. Give me one. 0, 0 is going to be on there. So you're going to build the graph without a calculator. That's how good you all are. Who can give me another point that's going to be on the graph of y equals the square root of x? 1, 1. 1, 1 is there. This is starting to look pretty linear. I need to give out some more points. Looks like the identity function from last week. What's another one? 4, 2 is going to be on there. So 4, 2, all of a sudden it's not looking quite so linear. Who can give me another one? Hands up, please. No? Because careful, what's the square root of 6? We don't know. You got to think, you don't know. 9, 3. If my input's 9 and I take the square root of that, I'm going to get out at 3. Now we've exhausted the points that'll fit on our limited Cartesian plane. Who can tell me another ordered pair, though, that's going to be on it? Terrific. Hands up, please. Let's keep it going. We've got some good momentum here, yeah? Next one.
36, 7.
And we can keep going. These are all our perfect squares. So the next one after that would be, that's 36, so that's 6, 49, 7, 64, 8, and 81, 9. Notice what's happening, though. It's not rising at the same rate. This is not linear. How far out do I have to go to make this graph rise up to 9? I have to travel all the way out to 89. So what's happening is this. You get this graph that starts here and slowly trends up. Oh, that's slowly trends up like this over time. Notice, by the way, that it's got arrows at the end because the graph continues infinitely to the right. What is the domain of this going to be? Hands up, please, if we can answer these. Because now I hope we're getting to the stage where we can really, really do these quickly. What do you want to say? Terrific. How about the range on this? The domain and the range are equal to each other. It's 0 to positive infinity and 0 to positive infinity. Take a look at the next one. Now, let's fill in the increasing and decreasing in constant intervals. Remember, increasing, decreasing, constant, we only travel, was it function Fred in here that went from left to right? Hands up, please, if you can tell me from where to where, from what x value to what x value, is this function increasing? You always use parentheses with them, and you've got to go from left to right. It just has to do with the notation issue and who writes calculus textbooks. Some people put the bracket, New York State does not. When is this decreasing? Now, this is going to be an interesting one. Remember what we said. You can tell me when they think this is decreasing. It's not. It's never decreasing, so we'll give it out as a null or empty set. When is this graph constant? Never. Now, remember, that's because we can only travel from left to right. You can't go right to left. How about the next one? When is the function value or y value greater than 0? For what x's is the function value or y value greater than 0?
Anything except for 0?
Nope. And it's how you set it. No? That's 2 now. You didn't get everything. You're not wrong, but you didn't give the most complete answer. 0 not inclusive of the 0, so open parentheses out to positive infinity. When is the function less than 0? Or when are the y values less than 0? Hands up, please. You can tell me that. We got 1, 2. Never. So we can give that out. Is the empty set. You could write DNE for does not exist. Who can tell me what when the function equals 0? 0. So we can give that out as a very limited interval from 0 to itself, or you could go through and give it out in set builder notation. When are the zeros of this function? Well, to find the zeros of this function, we would need to go through and set the y to be equal to 0 and solve. Looking at what we have here, the first thing I would want to do is recognize what my equation is, which is y equals radical x. Now I want to solve this, or find the 0, so I'd set it equal to 0. 0 equals root x. To solve this, I'd square both sides. Hopefully we know 0 squared is going to be 0. So x is equal to 0. When does the graph cross the x-axis? When x equals 0. There's an alternate way of viewing it, and sometimes the answer needs to be formatted this way. At what coordinate does the graph intersect the x-axis? Hands up, please, if you can answer that. At what coordinate does that happen? 3, 4 of us? Terrific. 0, 0. Either one of those is acceptable. Now we get into some great discussions too. How about the maximums of this graph? Think about that. Look at the graph as a whole going out to infinity. What are the maximums of this graph going to be? We've got 1, 2. What are the maximums of this?
Positive.
Now, what did you say, positive infinity? You're right and wrong at the same time. The question is, what are the maximums of this graph? There isn't one because it goes to positive infinity. A maximum has to be a value. Now we're going to talk about that at the end. This graph is unbounded above, meaning it rises forever. So what are its maximums? There isn't one because it goes to positive infinity. How about the minimums of this graph? Careful. We'll give it out as an ordered pair.
0, 0.
Yeah, the origin are 0, 0. Now, You've actually done enough now to answer this question out, and this gets to a great discussion too about something that a bunch of us missed when we took the test. We're going to take the inverse now. Looking at this, to take the inverse, I would need to switch the x and the y, so I start off with y equals radical x. Now I have x equals radical y. What do I do from here in order to find the inverse? I switch my x and my y. Felix, what am I going to say? So I get x squared is equal to y inverse. So I would normally go through and say that the inverse of this function is the squaring function, y equals the square root of x. But there should be a problem with that to you. I look at this graph right now. Remember that the inverse has to be reflected over the line y equals x. Who sees a disconnect or a problem with what's there, with what our inverse equation is? Think about what our inverse is when we graph it out. What's our problem, McKenna? The x squared, right? When I graph this out, it would look something like this. Is that our inverse?
No.
Kind of. What? From where to where am I going to look in order to take the inverse or to have the inverse function? We got 3 of you, 4, 5.
Bracket 0 to positive infinity.
That's terrific. And again, I want you to see this because so many of you are so used to, and I guess my personal opinion is, you guys, they treat you like little veal. You know what a veal is? Yeah, they keep it and they don't want it to ever do anything stressful. So they keep it like in a closed, like dark room all of the time for some unknown reason. But it never experiences anything. And that's what happens to you all. You have to understand that inverses, is it a really difficult concept to get? Sure. I don't want you to go through and grow up to be a cashier at McDonald's. I want you to grow up and build bridges and skyscrapers or planes. Or be someone who's smart enough to go through and make it so I can live forever. And you've got to understand that it happens by going through. You're going to try stuff. It's not going to work. Some of the concepts that we do are going to take a while. We did all of that factoring in the beginning because you didn't do it last year. So we'll take care of it. I don't make one excuse. If you need to do it, I'll cover it with you. But it, to me, is so promising that at least some of us now are seeing, why do we need to restrict the domain on the inverse? Well, because the other part, we get too much. Seeing that relationship is huge. And it's supposed to be a push. It's going to be tougher than zeros. Absolutely. But we're not going to shy away. I don't want you getting 71s again. And 68s. And having quarter averages in the 90s. That's a joke. That's a joke. I hate going through and having people say, yeah, I passed the course but failed the year. How? How is that possible? The test has a 20-point curve. A 68, in my opinion, is not so strong. If I got a 68, I take that as a personal failure on me. I want you to be so great. I want you to get 90s. And here's you are. I'm telling you. It's going to be disgusting how you do. And it's going to be funny. The highest grade that you're going to get on your Regents exam is the last Regents that you take. That's how good you're going to be. There's no pre-calculus Regents exam. Now, we can't answer odd, even. There's nothing we can do about asymptotes yet. Is this original function 1-to-1? Hands up, please, if you can tell me that. Is this original function 1-to-1? We got 6 of you, 7. What do you want to say?
Yes.
Why? The actual reason is because every input has only one output, or the outputs aren't used twice. Is this function onto? Some of you may remember this from last time. Does anyone recall if this is an onto function? No? No? We're testing the water? Onto functions are ones where every available output is used. Does this graph use every available output? What outputs does it use? Negatives, because you can't get an output of negative output from a square root. So is this onto? No. Not every y value. is used. Now, we can't answer these two questions here or here. This gets back to that question that we were talking about before Stephen answered. As x goes out to positive infinity, what are the function values going to? Positive infinity. They're unbounded above. As x goes out to negative infinity, hands up please if you can answer that second question. We've got 1, 2, 3 of us, 4. This should be going, this doesn't make sense. What do you want to say? No? You're close, you're on the right track. What's that? Yeah, it doesn't exist out there. Does the graph go to negative infinity? No, it stops at 0.
Okay, so that's starting at the origin. What if it goes to the positive?
Yeah, I mean, you're taking it way out there. Okay. You stop at positive, well, anytime there's a negative input, you don't get an out. You do get 1 from 0. Now, have your homeworks out, please. These are the answers to homework 2.1 that you had the other day. Make sure your name is at the top, please, with a -4 after it. Go through. If you've got questions on any of those, we got time to do maybe 2 if we burn through them quick. Check your answers to see what they are.
Tomorrow morning, okay? Sorry for tomorrow when you can.
Yeah.
Could you have a positive 5x and then you have a negative 2y?
You wouldn't because you don't, if you can take this cube root of the negative, you can bring that out. Okay? Any others? Yes. 14, all right. We'll do 14. We got time for one other one. 13 and 14. All right. Now, we'll bounce over to see 13 and 14. 13 is the cube root of 54y to the 10th. All right. What's the biggest perfect cube that goes into 54? Hands up, please, when you can tell me. Yeah. 27 times what? And then I've got y to the 9th times y. What can I take the cube root of? 27, which is 3. Y to the 3rd is y cubed. So this is 3y to the 3rd, and then the cube root of 2y.
I think that y to the 3rd is like 3 times 3 times 3 is 27.
Hang on. You're saying, which part did
So
you get
y
lost?
to the 9.
I'm sorry, the what?
Y to the 9.
Y to the 9th. The variables, you see how many times does the index go into that exponent. You don't take the square root or apply the same roots on it. Because remember, with exponents, when you multiply, you only add the exponents. Okay? And the other one we had a question on was, what was that? 14? Is that right? All right, so for 14, if we did out 14, I break that up into 100 times 2 times a to the 6th. That's a perfect square. B to the 7th is not a perfect square. How do I want to break that up? Perfect. That's great. B to the 6th times b. This, a to the 3rd. This, b to the 3rd. This is 10. That's how we got that answer. Now, let's do this. Make sure, please, that your name is at the top, and let's have you hand those up and over now with the -4 after it. And let's bounce over, please, to our notepad. We do have to go kind of quick now. Make sure your name's at the top. Let's hand those in and have your notepad at the top. Open to at or around page 6.
The bottom of page 6.
Bottom of page 6, all right. Now, what we're working on today the stuff that we're going through and working on today, we're going to work on adding, subtracting like radicals, and we do have to go kind of quick. In order for us to add or subtract radicals, we need to have like radicands, which is the value in front, and like indices. Excuse me, like radicands, which is the value under the radical, and like indices, which is the value in front on the perch. That tells you what radical you're taking. Let's take a look, please, at question number 1. I'm going to want to simplify these roots down. And we start off with root 27 and 3 root 12. What's the biggest radical, biggest perfect square that goes into 27? Hands up, please, if you can tell me. Biggest perfect square that goes into 27. Seriously? Really? Well, 9 times what? So I've got the square root of 9 times 3 minus 3 radical. What's the biggest perfect square that goes into 12? 4 times? 3, yeah. Take the square root of the 4, that's a 2. Square root of the 9, that's a 3. So this is 3 root 3 minus, what is the coefficient in front of my second root 3 going to be? Hands up, please, if you can tell me that. 6, because you take the product of these two. Uh-oh, what did I write wrong already? What a dummy. What did I screw up?
Root 2, not root 3. Or root 3, not root 2.
Yeah, root 3 here. Do I have like radicals with the same index value?
Yeah.
Yeah, the coefficients are different, but the index is the same. So what would I do? Well, just add or subtract the coefficients. What's 3 root 3 minus 6 root 3 going to give you?
Negative 3 root 3.
Next one up. Now we're working with perfect cubes. And again, it's not difficult, especially if you know your perfect cubes. Somebody in the first class, when we started listening out, we go, what are some perfect cubes? And somebody listed them off right away. Making them go, you're a calculator. No, they're not. They did their homework. Who can tell me the smallest perfect cube that we want to work with? Hands up, please. Nope. 8. Who can tell me the next biggest perfect cube? Hands up, please, when you can tell me. Who can tell me the next biggest perfect cube? That's 2, 3, 4, 5 would be 125, and it continues on. Looking at that, what's the biggest perfect cube that goes into 6? By the way, like indices, but not like radicands, so we can't do anything. 8 times what? So 5, and then the cube root of, this would be 8 times 2. Plus, now over here you've got 2 cube root of. How do I want to break down the 250? That's outstanding. Now, what do we do the last one? Well, you're stuck with it. Nothing goes, no perfect cubes go into 2. Cube root of 8, what's that going to give you, Jake? 2. What's the cube root of 125 going to give you, Jaco? So what is this going to simplify down to? Michael, what's the first piece going to give us?
10 cube root 2.
Second one, what's that going to give us? Cece? And the last one stayed the same. Looking at what's there, now let's work our way going across. Who can tell me what we would get if we went across and added or subtracted, whatever the operations are telling us? Outstanding. That's great. That's great. Questions on that? Now, here's the thing that we need to know. We actually already talked about this somewhat. You need to know that if I have a product of like radicals, I can put them under one radical or give them as 2. And I need to know that if I have division, I can give it under 1 radical or 2. They can always separate or go together if there's a product of 2 terms or a quotient of 2 terms. N just represents the index value. It works for every n value. Now, as we go through, we're going to have to understand this one here is the toughest one for you all to get. You can put them together or split them up with the quotient at any time. Take a look at the first one up. I'm going to take my product going across. That means I'm going to multiply my coefficients and then my radicands. So, Gerard, what do you get if you multiply your coefficients in number 3? And what do you get when you multiply the radicands? Now, I need to simplify that down, and I'm feeling very good about my chances. The x squared, y squared, I'm loving. What's the awkward part about taking the square root? The 12. Hands up, please, and tell me how you want to break the 12 up. 4 times 3, so this would be 20. And then root 4 times 3 times x squared times y squared. What can I take the square root of then that's there? What's that going to be?
2.
And? Which is? Okay, and then? So what are you going to give as your final coefficient? And what's the radicand? Terrific. Next one up. The same process applies. It's not any different. We're going to multiply our coefficients, and then we're going to multiply what our radicands are and simplify down. Olivia C., what do you get when you multiply your coefficients going across? And then I've got the cube root of, what would I have then? Now, one of those I'm really, really happy to see. The y cubed is looking great. I've got -2, and then the cube root of. Do any perfect cubes go into 30? 8 doesn't go in. 27 doesn't go in. We're past it. So this is going to stay 30. This is going to be x to the 6 times x, and then y to the 3rd. This becomes x to the 2nd. This is a regular y. So we would get -2 x squared y, and then the cube root of. Is that difficult for you? No. Now here's where we get into very awkward territory, because some of you, there's multiple ways that you can do this. Let's be clear, there's multiple ways that you can do this. In number 5, see how there's 2 radicals? When I look at this, I need to simplify it, or at least I see reductions that can happen right away if I house it under the same radical. So I'm going to rewrite this as 56 x to the 5th, y to the 5th in the numerator, all over 7xy in the denominator. Who can tell me what my radicand would simplify down to now that I've housed it under the same radical and I can do my reductions? We've got 3 of you. You can use the calculator if you need to. I don't care. And what do you get? Okay, and would that be in the numerator or denominator? 8 would be in the numerator. Keep going. Is there more you can do? And where is that at? In the numerator or denominator? Okay. And what about the y's? And it's all over 1. So really, do we need to have it over 1? So we get, now we're taking the square root of this. All of a sudden, this should be kind of easy. And I'm going to let us start doing some mental math. Who can tell me what's the biggest perfect square that goes into 8? 4 times what? So what would it simplify down to? 2, radical 2. And then what about these x's? What do I get if I take the square root of x to the 4th? And then? Terrific. Cube roots, we can do more of those. Take a look at question number 7. When we go through and do our question 7, this is the part where it gets a little bit awkward, because you've got to make sure you're always asking yourself what's left and where, because some stuff is in the numerator, some's in the denominator. I see this though right away. What coefficient is it really going to have in front of it?
definition then? What's the homework, by the way?
It's just out of that packet.
Okay.
It's the same one that's posted second day. So my coefficient's going to be a 5. Now I'm going to list all of this out. I've got 60x to the 5th y all over 12x y cubed. All I did was put everything that wasn't under radical, the same one. Now when I look at what's there, there should be a whole mess of simplifications that we can do. Who can tell me, hands up please, if you can tell me what's going to be left when I do some reductions on this and where. I've got 3 people, 4, 5, 6. Angel, what do you say? What's 60 over 12? Is that in the numerator or denominator? Keep going. That's in the numerator. Perfect. And I look at that, and all of a sudden this got really, really easy. I did my reductions. This got easy. Who can tell me what reduces out right now? Really? 4 of you? And? You see more? Now, part of this, I'm not going to say that this is wrong if you write it like this right now. All of these need to go out front, and that leaves me with a solitary 5 in the numerator, so just a root 5 there. What's in front of that? What's the coefficient going to be? Because some of us, we're going to lose track of things as we're doing this. We got 1, 2, 3, 4. Close. It is not 5x squared y. There you go. Because y is the y in the denominator, because when you took its square root, technically this is not a y, but rather 1 over y. Because the y squared was in the denominator of the radicand. Questions on that? All right. Now, next thing that we're going to do is multiply. Now, this is where, for some of you that do that, magic box of fun. I don't really know how to do it that way, nor will I show it to you that way. If it works, you can do it, but we don't show it that way. It's a double distribution of first outer, inner, last. So looking at what I have here, I'm going to multiply my first terms together. So when I multiply for these two binomials, my first terms together, what would I get? Lily, what would you have if you multiplied the first terms together? Okay, so we've got a 6. Now, what do I get when I multiply the outside terms together? Stephen?
3 times square root, negative 3 times square root.
Right, so negative 3, square root of 5. Now what about when I multiply the inside terms? Mike, what would you have? Okay, so positive 2 root 5. And now the last terms multiplied together. It's okay to do a little mental math here. Who can tell me what I would get if I multiplied my last 2 terms together, which would be these 2 here? We've got 3, 4 of you. 5. Come on, you're better than this. Terrific. Why is it negative 5? And where'd you get the 5 from? What's root 5 times root 5 going to give you? Square root of 25. Can we combine like terms? Absolutely. What would we have if we put our like terms together? Lauren? Careful. 6 and negative 5. What do they come together to make? Nope, 6 minus 5. 20. And what do you get when you do the 2 terms in the middle? Keep the coefficients the same. What's negative 3 plus 2? Negative 1. So I have negative root 5. Let's try for number 10. 10 is a special one. It's the quantity 5 plus root 3 and 5 minus root 3. Just so we're aware, because we're going to reference this in a second. How do those binomials compare to each other?
a simplified perfect square.
Yeah, I view it as this. Look at the left and the right binomial. They're the same except the sign in the middle changed. That's called taking the conjugate. That's really important. We'll show more about it in a minute once we get this done. Let's FOIL this out now. Logan, what do you get when you multiply the first terms together?
25, negative 25.
Nope. 5 times 5. 25. Now let's do the outside terms, and what do you get then?
15, right, 15.
Careful. 5 times root 3. That's 5 root 3. What about on the inside? Who can tell me what I get if I multiply the two terms on the inside together? 4 of us? 5. Minus 5 root 3 now. And what about my last terms? What would I have if I multiplied the last terms together? Negative 3. Now, something terrific happens right now. This should be easy. Because you look at this and you go, this is better than the last one. Why is this better than the last one? And this is a thing that I take issue with, that these 8th and middle school people tell you, nothing cancels, things reduce, okay? 7 over 7 reduces to 1, it doesn't cancel out to nothing, but they reduce away. Now I'm left with 25 minus 3. Who can tell me what my final answer would be? 22. What am I missing that I started with? The radicals. When you multiply something by its conjugate, the radicals are gone. So when we discuss conjugates, they're two binomials that differ only by the sign between them. So something like negative 3 minus root 5 has a conjugate of negative 3 plus root 5. All that you have changed is the sign in the middle. All that changed is the sign in the middle. Questions on that? Then let's keep going. You can't do one like 11. We'll do it kind of quickly. Looking at 11, I need to FOIL that out. What are my, and by the way, notice that they're conjugates of each other. My first terms multiplied together, Rebecca, what is that going to give me?
16.
What are the outside terms going to give you? Spencer? Multiply the coefficients and then the radicands. Positive 8 root 3. What about on the inside terms? Eva, what do you say? And the last terms, this is where people are maybe going to screw this up. How many tell me what you think you get at the end? No? Well, those two terms will, yes. But I'm saying, what do you get when you multiply the last two terms in the binomials? Why is it 12? Can you get it? 4, and then the other part's going to give you a 3. So this is going to be a negative 12. These reduce out, and I'm left with 16 minus 12, which is 4. Notice again, there's not a radical in there. That ties into how we're going to end for the day. And this topic is tough, and I'll tell you, I know it doesn't do us a lot of service to have 6 minutes to do them, but this is primarily, there's 3 of these on your assessment tomorrow, so you need to know how to do them. They're easy to do, and we've been building the components of this up. This has a radical in the denominator. You are not allowed to leave a radical in the denominator. We need to find something to multiply this by, so we're preserving the value, but removing the removing the denominator's radical. What you have to do is look at the binomial that's in the denominator. We have to multiply something by something that's going to cause that binomial denominator not to have a radical in it anymore. So we're going to have to multiply by the conjugate. Who can tell me what the conjugate of my denominator is going to be? Hands up, please, if you can take a guess. That's terrific. 2 minus root 3. And you can't multiply by anything other than 1 without changing its value. Yes?
Why can't you just multiply by that?
Because you'd still have a radical. You'd be left with 2 root 3 plus 3. Okay? Looking at what's there, we're going to just distribute out in the numerator. what would we have in the numerator, Teresa, if you distribute out the 5? There's a radical in the numerator, but who cares? Yes. This right here, 5 times 2 and 5 times. We're talking about this one here. It came from 5 times negative root 3. We have to distribute it out, because there's multiplication there. Now, when you go down and deal with the denominator, you've got binomials. Let's do it down in another area so it's not muddying up our work for this question. I've got 2 plus root 3 times 2 minus root 3. I'm going to FOIL that out right now. First terms multiplied together are going to give me 4. The outside terms will give me negative 2 root 3. The inside terms give me positive 2 root 3. Last terms together are going to give me a negative 3. You've got a reduction now that can happen. What reduction can we do? Those are now wiped out, and you've got 4 minus 3, which is 1. I wouldn't expect you to leave this as your answer. I'd expect you to give it as 10 minus 5 root 3. There's 3, I think, of these on your assessments. Well, this is what the Regents harps on. That's how easy they are.
Do we need to do the outer and the inner if it's multiplying by how much?
Not necessarily. I won't demand it. Because if you can recognize that they reduce out, you're fine. Take a look at over here on 14. What conjugate or ugly 1 would I use in 14? 1 person, 2, 3, 4. Come on. You can get this. What do you want to say? Terrific. We take the conjugate of the denominator, so this is going to be a 1 plus radical 5 and a 1 plus radical 5. Now from here, I'm going to go through. This is the part that's awkward because there's 2 different binomials that we're going to be working with. So this row right here, these 2 up front, you guys are doing the numerator. Do 1 plus root 5 times 1 plus root 5. There's going to be a radical left in what you did. You guys over here, you're going to do the other part, which is 1 minus root 5 times 1 plus root 5. Hands up, please, when you can tell me what you get when you do that out. And we need each other's components. So we got 1, 2 of us so far, 3 of us. What did you get, please?
1 plus
No. You've got to FOIL that out. List out all the terms. Careful, you're missing something. There's more that needs to be there. Do it out. Don't do the shortcut. First outer and last. There's 4 terms there. There you go. The numerator comes out to be 6 plus 2 roots of 5. What about my denominator over here?
Negative 4.
Negative 4. Now, looking at this, just so we're all on the same page, there's 3 coefficients here. You wouldn't leave this as a final answer. Does anybody know why? We can divide out of 2. So this would be 3 plus root 5 all over negative 2. I hate leaving a negative in the denominator, so let's bring it up top. So the negative of 3 plus root 5 all over 2, or some, you could distribute out the negative. If we needed to see this done out, 1 plus root 5 and 1 plus root 5, that's going to be 1 plus root 5 and then plus root 5 plus 5. That's why it's 6 plus 2 roots of 5. Now, I know it's a lot. Before you leave today, I'll give you this. If you want the answers, are we on 2-2? Yes. If you want the answers to your homework for tomorrow, open. Here's the answers for your homework tomorrow. If you want them, you can take a picture of it. That's fine. If you want the answers for your homework tomorrow and you want to take a picture of this before you go, that's fine. Oh, what the question was? I actually just wrote this out. I was more, if you can get that one done and try it on the homework. The Regents though, and the second ones are not that hard. They're like the first 1 and 2 that we did. Have a great day, kids.
Nap time.
We'll see you later.